We're going to look here at the Lindy liquefaction cycle on both a pressure enthalpy diagram and a temperature entropy diagram. And it's shown the cycle here that we're looking at, and just described in more detail in another screencast. But the idea is we take a gas that's close to room temperature and it enters a compressor, and the idea is that it has some entropy, and the entropy leaving we're assuming is the same. We're assuming, in other words, reversible compressor, but the temperatures could be higher, so we cool it down. Second compressor, same idea, and a cooler. Third compressor. We then go through a heat exchanger, the critical part of this process, to get to a low enough temperature so that when we go through the Joule-Thomson expansion, we get a liquid vapor mixture. We separate, remove the liquid, that's the objective, and we recycle the gas through this heat exchanger. It's at 1 bar pressure now, so we have to mix it with fresh gas, but the majority of the gas is in the recycle, and start over. So let's look at the pressure enthalpy diagram. In order to do that, let's look at the numbers that we're going to, locations on that diagram. And so what I'm showing here are the locations to the diagram for the cycle here, the pressures, the enthalpies at those points, the temperatures, and then for the compressor inlet and outlet, also the entropies. So these values we got from an equation of state spreadsheet uses the Ping-Robertson equation of state, and the spreadsheet then calculates the values for us because it is certainly not an ideal gas. So if we look now at a pressure, so we're plotting log of pressure on the y-axis, enthalpy on the x-axis. Should note that the pressure here is in megapascals, and so that then means that 1 megapascal, this would be 10 bar, tenth of megapascal is 1 bar. So we enter the cycle at 458 kilojoules per kilogram. This is 294. So that's this point here. That's 0.1 in the diagram. And what we're going to do is we're going to compress at constant entropy. And you can see these lines here that are labeled with the constant entropy lines. Compress it up to 5 bar. And so approximately it's something like this, and it goes off the scale. So we go through a heat exchanger at constant pressure. We get back to 300 Kelvin, as you can see the label here for the temperature. Then the cycle, the next compressor, again at constant entropy, we're going up to 25 bar, 2.5 megapascals, so something like this that goes off scale. And then at constant pressure, you're back to 300. And then final step is to 200 bar, that's 20 megapascals, again at constant entropy, so something that looks like this. And then at constant pressure, we cool it back down. We then go through the heat exchanger. Heat exchanger, we lower the temperature, in this case to 165. So we can see it's labeled here, this line 165. Remember, we like the enthalpy as low as possible because now we're going to go through the Joule-Thomson expansion, which is constant enthalpy. I tried to draw this as best I could. We're going to hit in the two-phase region. So we're going to hit here where we have vapor at this enthalpy, liquid at this enthalpy. So we need that H4, the enthalpy entering Joule-Thomson, to be between the liquid enthalpy and the vapor enthalpy at 1 bar, 77.2 K. Well, now we separate out this liquid, and we take the vapor, which is at 77.2 Kelvin, and we raise its temperature at constant pressure through the heat exchanger back to the inlet temperature that then the recycle enters again with some additional feed to the first compressor. Let's look now at a temperature entropy diagram. So this diagram's on a linear scale. Temperature on the y-axis, entropy, kilojoules per kilogram Kelvin. The constant pressure lines, now pressure is in bar, so this is 1 bar pressure. And these blue lines are constant enthalpy, so this is a constant enthalpy of 300 kilojoules per kilogram. So let's look at the process. We start 294, enter the first compressor. Going through the compressor, it's a constant entropy process, so we're on a vertical line, and we're going from 1 bar to 5 bars, so we're going to go like so. After the first compressor, we go through a cooler at constant pressure, cool back to 300. Second compressor, again, constant entropy. So it's a vertical line. We go up to 25 bar. And then We cool at constant pressure, so somewhere around there. So the third compressor, we're going to raise at constant entropy to 200 bars, so vertical line. And then we're going to cool down at 200 bars to 300 Kelvin. Next, at constant pressure, we go through the heat exchanger, and we get down to 165 Kelvin. That's the feed to Joule-Thomson. And so now we're going to go through the Joule-Thomson expansion. This is constant enthalpy, so it's along one of these blue lines, and where it would be is about here. We end up in the two-phase region. So that means we have liquid, 77 Kelvin. That's what we're interested in. We have the vapor at 77 Kelvin that we're going to send through the heat exchanger to bring it back up to 294 Kelvin, and we start the process over again.